Good day, my name is Sheng. Today I would like to present my final year project with the title of Tribological Characterization of Nanoparticle Enriched in Vegetable-Based Nanofluid for Machining Process. First of all, I would like to talk about the sustainability. It is the study of how natural systems function, remain diverse, and produce everything it needs for the ecology to remain in balance. And for the tribology, it is the science of controlling and managing friction, wear, and lubrication. So for the problem statement, since energy sources are getting depleted, so it causes to investigate new sources to replace non-biodegradable sources, and vegetable-based oil can replace petroleum-based oil. So the solution is additive added to formulate base oil to improve lubrication performance, also improve anti-friction chemical and physical properties of base oil. And for the objective, first one is to establish a new formulation of nanofluid from modified jatropha base with composite and activated carbon bamboo. Second one is to determine the physical properties of newly formulated nanofluid. Third one is to investigate the tribological properties of nanofluid through photo tests. Alright, so this is the scope of study. And for the summary review of journal, viscosity increased with the addition of minimum concentration of nanoparticles in nanofluid because the film is formed from the nanoparticles inside the base oil. Coefficient of friction is increased when the concentration of nanoparticles increase because it provides a thin lubrication film that allows the particle to change from sliding friction to loading friction. Friction torque decreased when the nanoparticles added because a boundary film that separates the metal contact decreases the direct contact in between the metals. Vesca diameter decreased when the minimum concentration of nanoparticles are added because it fills the valley at the sliding interfaces and establishes a thin powder lubrication film. So for the blending of additive, the reaction conduct at the temperature of 60 degrees Celsius for 1 hour. And this is the physical properties of MgO. And this is the properties of composite nanoparticles. One of the advantages is impressive tribological properties, and the thermal expansion coefficient is 5.1 times 10 to the power of negative 6 per Kelvin. And this is the properties of activated carbon nanoparticles. One of the advantages is cost effective, and the thermal expansion coefficient is 3.6 times 10 to the power of negative 6 per Kelvin. By comparison, activated carbon have the lower thermal expansion coefficient, which is better because it can provide better thermal stability. So this is the preparation of sample. Modified jatropha oil is non-edible oil. Copper oxide and activated carbon bamboo nanoparticles act as the additive, and the oil sample compared with the synthetic ester. And Unica Gene act as the synthetic ester are specifically used for the MQL method. So for the evaluation of physical properties, pygnometer are used to measure the density, while the viscosity cylinder is to measure the kinematic viscosity. So for the tribological test, there are 6 data collection that are done and are discussed in result part. And this is the example of image captured using the optical microscope. Once we get the outer diameter and inner diameter, we can use it to calculate the mean Vesca diameter using the formula as shown. So for the result part, viscosity. MgO is better than synthetic ester because of its long carbon chain is longer than synthetic ester that affected the viscosity and viscosity index. So synthetic ester show the bad lubricity performance because of highly viscous that form the thick film which produce more friction. Basically, nanoparticles in MgO sample created better stability of lubrication film that contributed greater value of viscosity index compared to MgO. MgO-A recorded higher VI, which is viscosity index, contributed stable lubrication performance due to the thermal expansion coefficient are lower compared to MgO-C. So lower viscosity contributed greater wear, while the high viscosity promote greater frictional loss and energy consumption. And high concentration of nanoparticles agglomerates due to the van der Waals forces that sedimented and become greater in size. And for the coefficient of friction, all MgO samples show the reduction of coefficient of friction compared to the synthetic ester because of the fatty acid of the MgO sample are able to stick to the contact surface. Nanoparticles fill the groove cause the reduction of contact pressure and the sliding friction change to the rolling effect. MJO-A is better than MJO-C because activated carbon bamboo nanoparticles consist of large pore which enough for the absorption of large molecules. So, low concentration of nanoparticles cause the poor result because of the insufficient nanoparticles to create rolling friction, while the 0.025% concentration of nanoparticles are enough to change sliding friction to rolling friction at the friction zone. Whereas the high concentration of nanoparticles cause poor result due to the agglomeration of nanoparticles that contributed greater particles. So for the friction torque, 0.025% concentration of nanoparticles provide the best result because of the nanoparticles easily fill the groove which allow the nanoparticles to roll and slide between the contact surface that reduce the friction. And for the mean wear scar diameter, MJO-A2 had higher viscosity due to the thick lubrication foam resulting with wear scar reduction. Composites are more thermally stable materials because of it consists of high oxidation number. So for the worn surface analysis, deep groove is due to the elimination of the lubrication foam provided by the fatty acid chain during the lubrication stage. And agglomeration of nanoparticles increased the stress concentration at the surface had caused the narrow motion between the nanoparticles. Material transfer is due to the broker of lubrication foam and the contact surface unable to be separated from each other. Shallow groove is due to the rolling effect where the nanoparticles roll between the surfaces. Rolling effect promoted the formation of thin firm layer provided good absorption ability, and the absorption resulting in reduction of wear and friction. So for the EDX result, MJO-C2 had the highest absorption of copper element, which is 0.72% in the worn surface, indicating can provide better lubrication foam layer. While the MJO-A2 had the highest absorption of carbon element, which is 8.22% in the worn surface. So for the surface roughness, MJO-A2 promoted smoother worn surface due to the shallow groove and small material transfer bring to lower surface roughness. While for the volume variate, MJO-A2 contributed smallest mean wear scar diameter and smoother worn surface that bring to lowest volume variate. So for the conclusion, MJO-C2 and MJO-A2 provide outstanding lubricant performance. So for the recommendation, first one is to apply another type of nanoparticle which is good tribological characteristic such as zinc oxide, silicon oxide, and titanium dioxide. Second one is to perform another type of tribological experiment such as pin on V testing, rod on ring testing, pin on disc testing, and ball on disc testing. Third one is to change the concentration of nanoparticles from 0.02% to 0.04% to get more accurate result. And last one is to apply another type of vegetable oil such as palm oil to substitute synthetic ester due to it contributed good anti-wear properties and reduced poisonous gases to the environment. So this is the Gantt chart of my final year project 2. That's all from me. Thank you.